here we are. We have some butt diagrams in front of us, which are really known as phase diagrams. It's just kind of a little more fun to think of them as butt diagrams. You can use your imagination and think about why we call them those. The first thing, and you've got a lot of information in your handouts. So these first couple slides you're not going to find in your handout, so you can just kind of follow along on the screen here. The first one, it says phase diagram of what substance? Well, first thing I want to think about is a phase diagram. What it does is it shows us the pressure and temperature that each of these pure substances can exist as. So every single pure substance has its own unique phase diagram. And it shows, for example, that you'll see this in all of these cases, that as you decrease temperature, and even especially when you increase the pressure, what would you guys expect that phase to be? At low temperatures and high pressures, what would that phase be? Anybody? Solid. So there we would expect a solid to exist. What about if it's at really high temperatures but low pressures? Gases. And then the middle point would be our liquid, is what we would expect. So that's what a phase diagram shows us, is where those phases exist. We can see some other things about them. We can see that there's always going to be one certain point that all three phases can exist, and that's known as the triple point. And there's also something known as a critical point, and I'll talk about that in a future slide. So that's the first thing that we notice here. This exact substance, I can look and I can see that right here along this line, this would be when the substance turns from a solid to a solid to a gas, or if it was going in the opposite direction, it would be going from a gas to a solid. So solid to a gas, that's known as sublimation. And at 1 atmosphere, and here's 1 atmosphere right here, so at 1 atmosphere and negative 78.5 degrees Celsius, we see that that sublimation takes place. Any ideas on what this substance is? CO2, dry ice. So this is an example of dry ice. So I'll bring this up again here in a little bit. Again, you don't have this one, but this is just another example of where we have standard pressure is being shown. Standard pressure. And so we know the different things that are taking place at each of those intersections, those lines. So we can think about at this point, or along this line, let me start with that. Along this line, that's when you have a solid that can turn to a liquid, which is known as melting, or you have a liquid that can change to a solid, which is known as freezing. Over here, we have a liquid that can change to a gas, which is known as vaporization, or a gas that can turn to a liquid, which is known as condensation. So if that happens at standard pressure, that would be these points right here. So we would know this, if you have it freezing or melting, that would either be a freezing point or a melting point, which could be anywhere along here. But when it happens at standard pressure, we consider that the normal melting point or the normal freezing point. So that's the temperature. That's the temperature that we would expect under standard conditions of pressure. And whereas this is our normal boiling point right there. So let's go to the one that you guys have. Okay, so you have this in front of you. And we can go ahead and label a couple things about it before we answer some questions. We already have listed, we've got solid, liquid, and vapor. And we can write those things down that we just saw on the previous slide. If you have a solid changing to a liquid, what do you want to call that? Solid to liquid is melting. Whereas liquid to solid is going to be considered freezing. Then we come over to our interface, our line between liquid and vapor, or liquid and gas. And if it's a liquid turning to a gas, we're going to call that vaporization. Okay. Hold on. There we go. And if it's a gas turning to a liquid, we are going to call that condensation. And then the last little line segment we have is a solid going directly to a gas without going through that liquid phase, and that's going to be considered sublimation. Everybody's seen that with dry ice. That's the real common one that we see. And what we don't necessarily see is the reverse direction, where it's that gas that changes directly to a solid, and that's known as deposition. We just don't happen to have those conditions that would exist at around here. So those we should know. We should know the triple point. And let's go ahead and put some information down here also. Let's go ahead and write down information about this point, which we're going to call the critical point. And you might want to write this down. These are going to be the conditions above which a distinct gas and liquid phases do not exist. Conditions above which distinct gas and liquid phases do not exist. In other words, no increase in temperature is going to cause that, or no increase in pressure, let's do that. No increase in pressure is going to cause that gas to liquefy. So it has no distinction between those. I think that's about it, except we still want to maybe mention something about this point, because that's going to be important for us. We're always going to be somewhere right around there, right around standard pressure. So because this is standard pressure, this is going to be able to give us our values for our normal points, and those normal points being this point right here, your normal melting or boiling point. Let's say melting point or boiling point, this would be our normal one. I did that wrong, I'm sorry. Normal melting or freezing point. And then over here, this is going to be our normal boiling point. We could also say condensation point, it's just not quite as common. So somewhere on your graph, I don't see it on here, but somewhere on that phase diagram, I think it probably tells you that this is a phase diagram for water. So we can see that, and if we come down here, it all makes sense to us. Our normal boiling point, yep, 100 degrees Celsius. Normal freezing point, it's going to be right around 0 degrees Celsius. So that is given to us as well. And then we can answer a couple things. You've got also some questions. They look like this. I'm going to read through the questions. I'm not going to fill it in here. I'm just going to look at this phase diagram, and you guys can fill in what you feel like is necessary. But the first one, it just says in this phase diagram for water what is being plotted on the X and Y axis. So you should know that this temperature is on your X axis and pressure is on your Y axis. Also, number 2, it says what does the line segment AB represent? Then it says what about BD and BC? So we really already labeled those, but AB, if I look at that, that is going to be, right here is AB. And we see that along there we've got sublimation and deposition occurring. So the way it's phrased, it says to explain in terms of equilibrium. It's up to you guys. You can just write sublimation/deposition, or you can mention that both solid and gas phases are present. Solid and gas, or sublimation and deposition occur. And then if we were to go along BD, and I don't know if this is going to let me curve my line or not. I'll try. Nope, it didn't. So I'll erase that. But along this line, oh, I'm really messing this up now. Okay, there we go. Technology. Okay, so along this line, what we end up seeing is that you can have both liquid or gas exist. So in other words, you've got vaporization and condensation. And then finally, along this line, you would expect both solid and liquid, or melting and freezing taking place. So that gets us down to number 5. And number 5, you should understand that point B is the triple point. And what that means is that you've got all 3 phases that exist at those pressures and temperatures. And point D, we've already explained that one, the critical point. And then we should be able to read this as well. It says, what is the temperature at the triple point? So you can come down here and easily just read these values, the temperature and the pressure. It asks for those. So 0.01 degrees Celsius and 0.611 kilopascals. And we've also answered the information about the normal melting point and normal boiling point. So we saw 0 and 100 degrees Celsius. And the reason that is because this value right here, that's our standard pressure. That's what we looked at to be able to come up with that. And then the last one, make sure you jot something down for this one. This is number 11. It says, and I'll flip to this real quick. It says, is the slope of the solid-liquid equilibrium line BC positive or negative? And what unusual fact does this tell us about water? So I am looking at this line right here. And what we end up seeing, what do you see about that? Is it positive or negative slope? Negative slope. And so what that does is that tells us something about the densities of these 2 substances, both solids and liquids. And what we end up seeing is that for water, and you guys know the answer to this because you see H2O in both of those phases all the time, that our solid is actually going to be less dense than liquid. Hopefully you're making neater notes than I am, but your solid phase is less dense than your liquid phase. So what you see as a result of that is that your solid, your ice, floats, and your liquid is going to be denser and it sinks to the bottom. Okay. When you look at phase diagrams, just look at that curve really quickly, and what you're going to end up seeing is that water is really one of the few, if only, substances that has that negative slope. The other ones are going to have a positive slope there. Okay, so now that, actually, before I do this, I'm going to go back real quickly, and you can't see this at home, but I have a vacuum pump in front of me, and in that vacuum pump, I have a beaker of water. So I'm going to say that that beaker of water, it's somewhere around 22 degrees Celsius here, and we're pretty close to standard pressures. So that's probably 22 degrees Celsius, and we're right in here at standard pressure. So I'm going to put us right there. That's where that water is right now. And I'm going to stop this, but I'm going to turn the vacuum pump on, and I want you guys to think about what's going to happen to, what is going to happen to this liquid that is in the vacuum pump if I turn the vacuum pump on and I decrease the pressure. So look at your phase diagram and think about that. Okay, so we just boiled water, 22 degrees Celsius still, straight out of the tap, and it started to boil because what we did was we took it from our 22 at standard pressure and decreased that pressure down to in here, and by doing that, it turned to a gas phase. So then a comment was raised about alternative, how you have different boiling temperatures and different things that you have to think about when you're at high altitudes, because at high altitudes, what's the air pressure like? Lower. You don't have that atmosphere pushing on you anymore, so it's going to be lower pressures, meaning, I can't find a color that's going to work. I'm using all these colors. Meaning, let's say you're right in here at lower pressures, right, when you're in the mountains cooking. So if you want to boil your pasta, you come along, what's going to happen is it's going to boil at a lower temperature. So what do you think that means you have to do with your pasta in order to get it cooked? It's boiling, it's cooking at a lower temperature, so what do you have to do? Cook it for longer. You have to cook that pasta longer because otherwise it's not, it's same like with hard-boiled eggs or something like that. So that's why you have to think about the air pressure that's involved when you're going through that. Okay. Now we want to just make sure we understand the distinction between boiling, or yeah, evaporation and boiling. And this is not on your paper either. So if you want to make a quick little note to yourself about it, but what we see is that evaporation, when this takes place, let's look at, I'm looking at this container right here. So in this container, you can think of it as a puddle that's sitting on the ground. It doesn't mean that it's 100 degrees Celsius outside when that puddle starts to disappear. That's not why it starts to disappear. But instead, these molecules that are right here near the surface, remember all of those molecules have kinetic energy to them. They all have different amounts of kinetic energy to them. The ones that are right here near the surface aren't bumping into near as many as the other guys are. So there's a little bit more room for these guys to move and escape, and they'll occasionally escape, and that energy is going to take them away as a gas. So what we end up seeing is that evaporation occurs only at the surface of the liquid, and it's going to be at temperatures that are below the boiling point. And this little graph over here is just showing you the example of how all of the particles, all the molecules in that sample are going to have different kinetic energies to them. And when we talk about temperature, we're talking about average kinetic energy. So you would be looking at that average, and even when you've got it below the boiling point, you can have some escape into the gas phase. So I'm going to go ahead and move on now. Next one. Here, if you, for my classes, I copied these two graphs on the back of your homework. You'll see them on the very bottom of the back of your homework. So that just shows you, and we really already went over this, you don't have this information written down anywhere else in your notes, except that you do have those two graphs, or similar graphs, I guess they are, phase diagrams. And what we end up seeing is, like we mentioned, that if you have a negative slope, then your liquid ends up being more dense. And if you have a positive slope, then that means your solid's going to be more dense. And so our examples that we see are carbon dioxide and water. And that's what we've, by showing these arrows in this example, we see that the arrows point to the more dense phase. And really what's happening is by increasing the pressure, you're just pushing those molecules, or those particles together. And so CO2, the denser phase, is going to be your solid, and H2O, it's going to be your liquid. Okay, this takes us to intermolecular forces, and we have a whole bunch of stuff to cover, so I know I feel like I'm going kind of fast with this, but there's a lot of material that's all related. Okay, especially you drivers out there, but anybody really can answer this. Inter, think about what that means. If you're driving on the interstate, what does that mean? Between, right? So inter is going to be between. If we're talking about intermolecular forces, we're talking about forces that are between the molecules. We haven't really talked about this yet. This is going to be new, intermolecular forces. What we have talked about is something known as intramolecular forces. Of course, we did not call it that because that's just a silly name, but it would be the forces that are what? Within the molecules. What do you call those forces within the molecules that are holding the molecule, that within one molecule? What's holding that molecule together? Bonds. That's exactly what it is. So if I were to ask you, what is stronger? Intramolecular forces, which are bonds, or intermolecular forces? The answer would be intra. The bonds are going to be really, really strong, holding those things together. So if I had H2O, I can give it some energy and overcome some intermolecular forces, have it turn into a gas phase. That's pretty easy, but to give it enough energy to have it overcome the bonds, the intramolecular forces, and break down into the hydrogen and oxygen is going to be much more difficult. Okay, you have your paper in front of you that has 3 intermolecular forces that are listed. The first one we're looking at are dispersion forces, also known as London dispersion forces, based on somebody's name. These guys are going to be the weakest right here. And they're so weak because they only occur in nonpolar molecules. And if you think about what a nonpolar molecule looks like, let's think maybe Cl2. I have some chlorine bonded to another chlorine. There's our Cl2. Does either of these guys have a greater share of the electrons than the other? Nope. They're just exactly the same. So what we end up seeing is that there's no charge. There's no positive or negative side to that molecule. So when another Cl2 comes along, is there any great attraction between those two molecules? Not really, because there's no positive and negatives. What does happen, though, if we read through this, we see that there's something known as instantaneous dipoles that can be created. These are kind of like fake charges that are created because these electrons are constantly moving, constantly in motion. It might be just for a quick instant of a second, fraction of a second. This chlorine right here might have a greater share of the electrons. Next fraction of a second, this guy has a greater share. It's constantly changing, but never a whole big amount is it going to differ. So because of that, you might get a little bit of attraction. They easily overcome that pretty quickly. Therefore, what phase do you think that we're going to see a lot of these things exist as? Gases, right, because they're overcoming those molecular forces, those intermolecular forces, and they're heading their own way. So I'm going to say many or most exist as gases. Because they are so weak, there's not much of a force holding them together. They tend to go their own way. This could be, I could do something like neon, and we could see that neon hanging out next to another neon. Well, there's no great attraction between those guys. So noble gases, a lot of our diatomics would be examples. Those are all going to be nonpolar. And so, therefore, we would expect them to just have dispersion forces holding them together and be very weak, and they exist as gases. Okay, then we move on to dipole-dipole. And while we're at it, let me just flip to this one because you guys have this all in a nice, neat row on your sheet. Hydrogen bonding, you can make yourself a note that this one is the strongest. Dispersion forces was the weakest. And so dipole-dipole is going to be right there in the middle. And what we see is that dipole-dipole forces exist between polar molecules. So there are actually poles that are created. So if you had something like hydrogen chloride gas, we'd look at this and we say, wow, chlorine has a much greater share of the electrons. So therefore, he is going to have a more negative charge to him, whereas hydrogen is going to have a more positive charge to that side of the molecule. That's just a funky little symbol that's showing those dipoles. It's just showing the charges on each side of that molecule. So when another hydrogen chloride molecule comes along, who's going to want to hang out next to the positive? The negative. So you have hydrogen chloride, and there's an attraction there between the negative and the positive. So there is actually an attraction holding those things together, and opposite charge resulting from attraction between those guys. Okay, so this one's definitely going to be stronger than your London dispersion forces. And then finally, your hydrogen bonding, and this is a little bit of a misnomer. It's really not bonding. It's just intermolecular forces holding those molecules together. But it's going to happen for the exact same reason as dipole-dipole. It's just an extremely strong dipole-dipole force. And it's extremely strong because it's hydrogen that is bonded with nitrogen, oxygen, or fluorine. And if you want to look on the periodic table there, you see hydrogen, when it is bonded with nitrogen, oxygen, or fluorine, you see nitrogen, oxygen, and fluorine in the upper right-hand corner, extremely electronegative. So these guys are very electronegative, give up or grab those electrons very, very easily. So because of that, it makes a really strong, it's about 10 times stronger than just your normal dipole-dipole force. So whenever you've got hydrogen bonded with one of those three extremely strong electronegative atoms, then you're going to have a hydrogen bonded force going on. The other thing to think about, because it's so strong, what do you think that means as far as boiling points? If I want to get it to break apart, what am I going to have to do? It's going to be much higher. So these guys have higher boiling points to be able to overcome those intermolecular forces. Okay, so now we can look at a graph like this, and we can see that this relates our boiling point to, it shows us atomic numbers, but really what we can see from something like this is here I've got hydrogen that is bonded with oxygen. Here I've got hydrogen that is bonded with nitrogen. So notice that all of these, for example, are in the same group. All of these are in the same group or family. But because this is hydrogen bonded with an extremely electronegative element, these boiling points are going to be much higher than the other ones that are in the same family. As you increase that atomic number, though, it does increase its boiling point. So what we might want to just write down here is that they have high boiling points due to hydrogen bonding. And so then we can look at something known as vapor pressure, and it tells us up at the top what that is. It's the pressure due to particles of a substance in the vapor phase above its liquid in a closed container at a given temperature. And the weaker the forces holding the liquid together, the higher the vapor pressure of the liquid. So really what we're thinking about is that interface again between the gas and the liquid. So if we wanted to figure out what is our normal boiling point for each of these substances, and think about that really as being your line between the gas and the liquid, what you end up seeing, well, if it's normal boiling point, I have to think about my standard pressure. That looks like 760 millimeters of mercury. So at standard pressure, I come along here and I can read these values down here and there. So we see that Br2, I'm going to call that 35 degrees Celsius. What's your water at, H2O? 100. And CH3Cl is going to be, let's call that 80 degrees Celsius. Well, as we look at this, we notice, I'm going to jump over to water, the familiar one. We see that our water is 100 degrees Celsius, so that's going to be the really high one. What else do we notice about this? Hydrogen bonded with oxygen. So what intermolecular forces does it have? Hydrogen bonding. Whereas if I come over here to my Br2, my bromine, this has a much lower boiling point. So this is what we're seeing. Low boiling point. This is a really high boiling point. And our bromine is going to be a much lower boiling point because what type of intermolecular forces? Dispersion. That's all it's got is London dispersion. And then the middle point, here we have a polar molecule, but hydrogen bonding is not taking place. So because of that, we are going to call that dipole-dipole. Okay, so now we see how there's a relationship between boiling points and intermolecular forces between these substances. Okay, so now we're moving to something even completely different, and we're looking at solubility of these substances. So you have this information on your sheet, my students, it's the upper right-hand corner, and we can talk about solutions as being saturated, unsaturated, or supersaturated. Maybe you can draw yourself a nice little small little graph that looks like this, because what you'll see is you'll have a curve on your graph, and meanwhile this is solubility here, and this is going to be temperature here, is what you're going to see. And if we were to look at that temperature and the amount, the mass of your solute per grams or kilograms or something of your water, if it fell on the line, that is considered soluble. If it falls under the line, then that means you can still put more of your solute in there and it'll still hold it. So that's considered, oh sorry, I wrote that wrong again. That's considered saturated. If it's under the line, then it's considered unsaturated. And if it's above the line, then it's considered supersaturated. And I'm not going to read through each of these, but we will see some examples as we go through these next couple problems. Okay, this you find this chart, my students, on the back of your homework. So you've got a solubility curve that you'll be needing this for your homework, for example, and you just have to learn how to read it. So the first question that we have here, it says, at which temperature do sodium nitrate and potassium nitrate have the same solubility? So when I look at those guys, here's my sodium nitrate on this line and my potassium nitrate on this line. So when do they have the same solubility? Yeah, you guys can come up here and see this is where they cross. Now, again, you want to make sure that you understand what your axes are telling you. This is the grams of solute per 100 grams of your solvent is what that's telling you. That's your solubility. And down here we have temperature, and it's given to us in degrees Celsius. So I would answer this. I'd come on down and I would see that it's right at 70 degrees Celsius. Okay, next one, it says we have 100 grams of water saturated with potassium chlorate, and it's cooled from 50 to 30 degrees Celsius. So I find my potassium chlorate, and it goes from 50 degrees to 30 degrees Celsius. So we want to know how much of that solid crystallizes out. So we look at it and we can read, and this isn't going to be exact here, but on yours you'll see it better, that in this case at 50 degrees Celsius we see that it can hold 21 grams, but at 30 degrees Celsius it can only hold closer to what? 11-ish. So when you decrease that temperature, that means that solid has to fall out. It's going to precipitate out or crystallize. And so that's going to be somewhere around 10 grams that is going to crystallize. And number 3, how much ammonium chloride is needed to saturate 50 grams of water at 35 degrees Celsius? So this should catch your eye, that that's not the same as that. So the way I think I'd start this is first try and find my curve, which is right here. So we've got our ammonium chloride, and we are looking at 35 degrees Celsius. So I'd say right in here, I come up, I see this point right here, I go over and I read that value, and I read that as 40 grams of our potassium chlorate, and we could write that if we want. But that's 44 grams per 100 grams of H2O. That's not the question. The question is, what about in 50 grams of H2O? This one was easy enough that you guys probably just do this in your head, but some of the ones that you would do on your homework, you might want to make sure you have this method down because it'll be easier this way. So now you've got it like this. You just do the math, and that gives you the mass of your potassium chlorate that can be saturated in that volume of water. And the answer is 22. Okay, just a couple more. Okay, we're still trying to read this curve. And here it says, assume that all of the following can form saturated or unsaturated or supersaturated solutions. And we just want to be able to read these curves. So I'll do this first one, and we'll just kind of remember that you understand this concept right here. So that's all you're doing with these guys. Is you're saying if you had potassium chloride, which we find right here, and if we had in 100 grams of water, we had 40 grams at 80 degrees Celsius. So 80 degrees Celsius and 40 grams is right there, I believe. So what would you call that? What I didn't hear. And it's below the line, so unsaturated. The next one, what you're going to see, I'm not going to go through it, but you guys are going to see it's super saturated. And then the last one, it's kind of close to the line. I'm not sure if that was originally the intent, but I'm going to call it, instead of calling it saturated, I'm going to call it slightly super saturated. And that is all we have. And this just shows you some of your figures that you have that you'll be needing to use on your homework.